So here we're going to explain electronegativity, how it works, and what the trend is across the periodic table, specifically for the atoms that we tend to be concerned with for organic chemistry. So we've got boron, carbon, nitrogen, oxygen, fluorine, fluorine down to iodine. That's what we're going to be looking at. And so you may already know the trend, and hopefully you do. As you go to the right across the periodic table, things generally get more electronegative towards fluorine. And then as you go up the periodic table from the larger atoms to the smaller atoms, also getting more electronegative. Right, so we have that trend where you can kind of predict relative electronegativity. And fluorine is the most electronegative, but what's the deal with fluorine, right? So just as another reminder, electronegativity, this is the strength of the pull that a nucleus has on its atoms. And that nucleus part is kind of the key. So how tightly is it going to hold on to electrons? And this could have to do with bonds or just atoms on their own. But again, what's so special about fluorine? Why is it the most electronegative? Why is it any better than oxygen or chlorine or bromine? And there's two main things to look at where we can use that trend and then predict it. And one is if we're going across the periodic table, we're roughly comparing atoms that are the same size. Right? When we say that, we say between carbon to fluorine, they're around the same size electron shells. Right? So our carbon atom here, its nucleus has 6 protons. Right, so 6 plus charge. And then it has its 6 electrons. If we're mostly just thinking of the valence, right, the valence shell is in the valence electrons are in the 2s and the 2p shell. Same for fluorine, it has more protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And its electrons fill the same shell. So that's why we say they're roughly the same size. Realistically, actually, because of its electronegativity, fluorine is actually a little bit smaller. It squeezes those electrons in a little bit tighter, but we'll call them around the same size. So if we're saying, okay, I've got an electron here, how tightly, how strong will that be pulled towards the nucleus? Well, it should make sense then that the more protons you have, the more positive charge you have pulling in and grabbing onto those electrons, the more tightly held it's going to be, right? So basically, if they're all the same size, you're going to have a stronger pull, right? So you've got more protons. Is going to be a stronger pull on those electrons, right? So again, this is for if they're around the same size electron shells, because as we know from the trend, if we go down the periodic table to bigger atoms, which definitely have more protons, they're less electronegative, right? So we can explain that as well. So let's pick bromine as our example. Kind of goes naturally down, but let's put it over here, right? Bromine has 35 protons. Which is a lot more, so way more protons than fluorine, but still not as electronegative, right? So why is that the case? Well, our electron shells are going to keep filling here, so bromine, 1, 2, 3, 4, right? That valence electron in bromine is in the 4s and 4p shells. So it's much farther away, right? And so again, if electronegativity is the pull that a nucleus has on its electrons, the further away those electrons go, the less electronegative it's going to be. And so we've got two factors going on here. You have number of protons and distance from nucleus, right? So that's the two things that we have to factor in to kind of decide whether or not something's electronegative or not, or more electronegative or less. Right? How many protons has it got, and how far away are those electrons? Because from the trend, the smaller atoms with less electron shells generally ended up more electronegative. As we go down to bromine, yeah, I got way more protons, but they're further away. Not only are they further away, but this negative interacting with this positive in center is blocked by all these other electrons in the center. So that's called electron shielding, and all these other electron orbitals will also shield the valence from its electronegativity. And again, chemistry, we always talk about valence electrons because they're mostly the ones that do all the chemistry, and that's because as we get closer, those ones are held on really tight. All right, so that's our basics for electronegativity. We're looking at the difference in how far away the valence electrons are and how many protons the atom has. And that explains our trend.